Okay, good morning, everybody. Welcome back from Reading Week. So picking up from where we left off, we're now in the declarations notebook. There's not a lot new here. There's something new about when we declare a function in C compared to what happens in Java. But otherwise, most of the stuff here should be review for you. Okay, so a declaration is simply saying that a name exists. That's all that the declaration is in C. Right, so a declaration introduces one or more identifiers. An identifier is just a name. So for example, you have to declare a variable in both C and Java before you can use the variable. Right, so you know you have to do stuff like this, right, in both languages. Now in Java, if you do something like that, it's legal. But if you try to use the variable X or Y in this case on the right-hand side of an assignment statement, the compiler will complain. Right? It'll tell you that your variable is uninitialized and this is an error in Java. In C, that's not the case. So in C, you've declared the variable x, y, and a, b, c. They all exist. They don't have any set value yet, but they exist. So there's a chunk of memory labeled x, y, a, b, and c. There's some bits in that chunk of memory. It'll have a value. So if you try to use the value for some reason, for some purpose, the compiler will happily let you do that. But remember, the value is uninitialized. So here, is a program that does exactly that. There's x, there's y, there's a, b, and c, and then it actually tries to print out the value of x, y, a, b, and c. If you try to do this in Java, Java won't let you do this. The compiler will say that the variable is uninitialized. In C, depending on your compiler may issue a warning saying they're uninitialized, but the program will compile and run. So if you run that, you get a bunch of compiler output here, and they're all warnings, right? And they're all something like x is uninitialized, right? But the program does run, so you get past all the compiler warnings, and it does produce some output. And notice that, in fact, x, y, a, b, c, they all are, in fact, uninitialized, right? So x is some strange value here, y is 0, and c is 0, which is strictly a coincidence, right? They're not guaranteed to be 0. If you assume that they're 0, there's a good chance your program won't run correctly. So of course, you should normally initialize your variables when you declare them, right? Not always, because sometimes you have some sort of statements afterwards that set their value. But it's usually a good idea to initialize their values when you declare them. And so this is called definition in C, right? And so when you declare and define a value, the values are set to specified initial values. Okay, we saw const briefly earlier. Const simply means that a variable is read-only. So similar, but not exactly the same as final in Java. Right? Final in Java means you can give it a value once, and then it's read-only. In C, it means it's read-only, period. So if you want to, if you create a const variable, you have to initialize it. Otherwise, you're stuck with whatever value you get at random. Right? So here, const x, int x1 means x is the constant 1. Right? This is problematic. Constant y says y is constant, it's read-only, and it has an unspecified value. Right? If you try to fix the problem by assigning a value to it later, that doesn't work. Right? So here it's a compiler error. Right? And the error is assignment of the read-only variable y. Right? So that doesn't work. So const in C is part of the type. So the type of x is not just int, it's const int. Right? And the type of y is not just int, it's const int. All right, so functions are the only thing that are different regarding declarations in C and Java. It's the only thing that's significantly different. And so a function declaration simply says that a function exists, it has a return type, and it has some parameters. Right? And so there is a semicolon here, but again, Jupyter is not rendering the notebook correctly, so I don't know what's going on here. So there's a semicolon at the end of this statement here. That says that the function max2 exists. It takes in 2 double values, and it returns a double. The definition is not here. So we don't know how max2 is defined. Presumably, it returns the max of x or y. X and y, sorry. You can still use this function in a program, even if you only have its declaration. So here's a program that declares max2, right there. Right? Doesn't define what max2 is, but in the program, it actually uses max2. Right? It uses max2 in the function max3. So max3 is defined. Right? Returns the max of x, y, and z. It's defined in terms of max2. Right? So you compute the max of x and y, and then you compute the max of that value in Z, and that returns the max of 3 values. Right? So this program will, you can compile this, but you can't turn it into a runnable program because it's not a complete program yet. Right? It's not complete because we're missing the definition of max2. Right? So can you compile this program? The answer is yes, but you can't turn it into a runnable program. So to compile the program, you want to use that -c option that I talked about like at the beginning of the week before reading week. And this compiles your file or your compilation unit into object code, but it doesn't link. Right? So remember in the linker stage, that's the stage of compilation that's going to try to find the missing definition of max2 and stitch it into our program. Right? You can still compile it using that with -c here. So if you go into the directory with the notebook, so here's uses max2, right? You can in fact compile this, and the compiler is perfectly happy with it. So that compiles down to object code. There's no runnable program yet, right? So somewhere we still need the definition of max2. And this is a very common occurrence in C programs, right? It's very common that you write a program and you split up your definition of your functions or your code into several different compilation units, right? Similarly, you might want to use somebody else's library of code. So they'll provide you with some probably pre-compiled object code, and then you want to link to their library, right? So the definition lies outside of the code that you're writing. So to complete the program, we have to define max2 somewhere, right? And so I'm going to define it inside of another file, right? So I'm going to make a file called max2.c, which is right there. Right? If you look at what's inside max2.c, right, you see there is the definition. Oh, sorry. There's the definition of our function max2, and that's all that's there. Right? There's no includes. There's nothing. Excuse me. There's nothing else other than the definition of max2. Right? So you can compile this as well into its own object code. So if you do gcc -c max2.c, again, the compiler is perfectly happy with that. Right? It's not a complete program on its own either. There's no main function. So if you just try to compile max2 without a compiler option, right? So remember what happens with GCC, it tries to produce a runnable program, right? And now it complains, it says there's no main function, right? So this is not a complete program either, right? Okay, so there's max2.0, so that's the compiled version, that's the object code version of max2. There's uses max2.0, that is the object code version of uses max2. Right? If I can mash those two things together, that will produce a complete runnable program. And there's lots of ways you can do that. So here I can do gcc uses max2.0 and max2.0. Right? And so now the linker runs, stitches the two files together to produce a complete program. And this it calls it a.out in this case, because I didn't give it a special name. Right? So I can now run a.out. And I forget exactly how I run the program. Sorry, just a second here. Okay, so this is going to compute the max of 5.2, 1.3, and 4.9, I guess. And there you go, right? So it tells you the max of the three values is in fact 5.2. Right, so we've taken two separate compilation units, right? Neither of which constitute a complete program, right? We can put them together and to form our complete program. And so that's what the notebook walks you through. There's multiple ways that you can stitch the programs together, right? There's one way to do it, right? So that's the way I just showed you, right? Alternatively, you can just compile all of the original source code files together on the command line, right? So you can compile max2.c. Uses max2.c, right? And together, those two files constitute a complete program. And so the compiler will then stitch their object code versions together into a complete program, right? And there's other ways you can do this as well. So there's many ways that you can do. You can form a complete program from multiple different files. All right. So that's a very simple example of splitting up your program into multiple compilation units. Now, when you do this, you have to be a bit careful about what's going on. Okay, So when you declare a function in one file, declaring functions defined in another file is error prone. You can't always do it if the source code for the other file is not available. Right? So instead of declaring the functions, so for example, sorry, back here. So inside uses max2, I manually declared the definition of max2. You want to avoid doing this, right? Like this would be awkward if you had to do this all the time. So imagine you wanted to use the standard library and you wanted to print stuff. If you had to manually declare printf every time, that would be a real pain in the butt. And so it's also very error prone. So instead of declaring the functions, a common mistake that new programmers will make is that they will simply include the other file. Right? So I've already shown you how to include something. If you remember what include does, it drops the contents of a file into your program. So someone who's writing uses max2 might say, well, I don't know what max2 is, but I have the source code for it, so why don't I just drop it into my program? Right? And so this is very common, and I'm sure some of you are going to do it on assignment 4. Maybe 5 and 6 too, who knows? Right? So you'll include the source code file into your program, and this causes all sorts of problems. Unfortunately, it doesn't cause a problem in a simple case like this. So if you do it here, everything's fine. It'll actually work. Right? So remember what happens here. You get the definition of max2. Right? This uses max2. Everything's fine. Right? So this will actually work if you do this. And so this is what causes new programmers to repeatedly do this, even though it's incorrect. Right? So it works if you compile your program like that. Right? If you try to compile it some other way, though, right? So for example, as soon as you try to compile, let me show you on the command line directly. Okay, so I'm going to compile, so let's first look at, whoops, sorry. Cat bad. Okay, so there is the program I just showed you. It includes the source code for max2.c. So if you just compile this like the following. Right, so I'm only going to compile the one source code file, right? Even though max2 lives in a separate source code file, right? This actually works, right? It works because the include statement drops max2.c into your program right here. So max2.c is defined, everything's fine. Right? Now, if you were paying attention to the previous discussion of stitching two programs together, you might say, oh, I have to compile max2 as well. And so when you try to do that, like that, right? Now your compiler complains, right? LD is the linker, and so this is a clue as to what's happening, right? And so the linker is saying, hey, max2 is defined more than once, right? And so what's going on? Right? So what's going on is that the include statement here drops max2 into your program right here. You're now going to try to compile and link to max2.c, which also has the definition of the max2 function. So you've now got two functions called max2 in the same program when the linker tries to run, right? And you're not allowed to do that in C, right? You can't have two things with the same name in C. And so now the linker complains. It says you have multiple definitions of max2. So that doesn't work. Right? If you try to compile them separately, right, both files will compile separately, no problem. But as soon as you try to link them in the third step here, you'll get the same error again, right? Multiple definitions of max2. Right? So in C, the names of all functions have what's called external linkage. And so the names of the names of everything having external linkage, they must be unique across your entire program, right? So there's two functions in our program called max2, right? That's not allowed. So the solution here is to take the declaration of max2, right? So remember, to compile your program, all you need is the declaration, right? And so what you want people to do is you want people to have the declaration. You want the people to have the declaration, but you don't want them to have multiple definitions of the function itself. So what you can do is you can create a header file, and the header file contains the declarations of the functions that you want to share with other people. So we have a file called max2.h. Right? .h is the standard extension for header files in C. Right? Inside the header file, you have only declarations. You never have a definition. Right? So there's my declaration of the function max2. Right? The definition still lives in max2.c. Right? But to compile, but for people to use max2.c, all they're going to do is they're going to include the header file. They're not going to include the source code file now. Right? And so by not including the source code file, that avoids the the multiple definition of a function problem. So in max2.c, you can include the header file. You don't have to, but it's good practice to include the header file. Right? Anybody that wants to use max2 now includes the header file max2.c. Right? Max2.h, not max2.c. Right? Don't include the definition, include the declaration only. Right? And now when you compile all this together, everybody's happy. Okay, there's some new stuff here. There's this if, and, def, and define preprocessor statements. Also an end if. Right? So if and def means if not defined. Right? Max2.h is just any name that you want to give it. Right? This says if the symbol max2._h is not defined, right, then everything inside here gets processed by the preprocessor. Right? So the next statement says define max2.h. Right? So if max2.h is not defined, define the symbol max2_h. Right? So the next time the preprocessor sees this line here, right, it'll say, oh, max2_.h is already defined. It'll skip over everything between the if and def and the and if. Right? And so it'll end up down here. So it won't include the declaration a second time. Right? And so this structure here, and I guess including the end if, is what's called an include yard. Right? It prevents the contents of a header file from being included into a program more than once. Your header file should always have an include yard. There's other ways to do this. This is just the way I do it. This is just the way it's done in this course. So the include yard introduces it's just a dummy identifier, right? So it introduces the identifier max2.h that the preprocessor is going to use to determine whether or not the header file has been included already, right? There's no standard for giving the name, for defining the name. So I always use the name of the header file in all caps, right, with the period replaced with an underscore. Okay, so if the header file gets included more than once in the same program, in the same compilation unit, and you don't have the header yard, depending on what's in the header file, this might cause problems with your program. So it's always a good idea to have the header guard there. If all you have are function declarations, it probably doesn't matter. But if you have some variables that are declared in the header file or other things, it could cause a problem if the header file gets included more than once. So it is considered good practice, and it's considered important to always have an include yard in your header files. Right? And so that lets you split up your program into multiple separate files. By having the header files, that prevents the problem of having to include source code files, which introduces the problem of having multiple definitions of the same functions. All right, so that's the declarations notebook. Any questions? All right. So the next notebook is the statements notebook, and this is, again, largely review, I think, for most of you. Okay. Okay, so statements in C are things like if statements, loops, and things like that. Right? So they're just parts of your C program that are executed in sequence. Right? So assignment, you all know what assignment is, right? X equals Y or something, or X equals 5 or something like that. Right? So the exact same syntax as in Java. The big difference that you have to remember is that if you have an array, if you have an array with automatic storage duration, you cannot assign to that array variable. Right? So here is an array, like right there. Right? There's my array variable X. Right? Here's an array variable y and its array. Right? In Java, you can write x equals y and everything is fine. Right? In C, you cannot. Right? So in C, this produces an error. Right? And it even tells you that it's an assignment to an expression with array type. Right? So you cannot assign to an array variable. You can initialize one, but you can't assign to it. And so you might wonder why this is the case. So why does it work in Java? Right? So remember, in Java, arrays are just array variables are reference variables. Right? So they store a reference, right? So a memory address. So when you write x equals y, you're simply saying the value stored in x is whatever memory address y is. Right? So you're effectively saying x and y now point to the same array in Java. Right? In C, this isn't how it works. So in C, an array variable is not a reference variable. Right? It actually stores, you can think of it as storing the values 1, 2, and 3. What's happening is that you have an array in memory, so you have a 1, and then beside it there's a 2, and beside it there's a 3. Right? And the x you can think of as pointing to the first value in the array. So you can think of it as pointing to the 1. Right? And so when you write x equals y, as far as C is concerned, you're trying to assign the value of y to x, right? Which looks like you want to copy the contents of y into x, which is not allowed. Right? One of the reasons it's not allowed is because the compiler doesn't know how big the arrays are. Right? So remember, in C, the compiler doesn't keep track of the size of the arrays. So even if you wanted to allow something like this to happen, you can't. Right? The compiler doesn't know how many bits to copy from x into y. So this isn't allowed in C. The problem with this in C is that strings in C are just arrays of char. And so that means you can't copy strings like that. Or you can't assign a string to another string. Right? It doesn't work. You're trying to assign an array to another array, right? Which is illegal in C. So that's annoying. So in C, if you want to copy a string, you have to either write a loop, copy the characters out of the one array into the other array, or you have to call a function to copy the string for you. Languages like Python and Java avoid this because they are strings and arrays are reference types in those languages. Right. Function calling works exactly the same as in Java and Python, except you don't need the name of a class or object. Right. So to use sign, you just include math.h and then call sign. Right. Same with cosine. Oh, we haven't seen define yet. No, we did see define. So the preprocessor has a command called define. So define, if you just give it a name, it simply introduces a new name that the preprocessor knows of. Right? So here, m underscore pi tells the preprocessor that the symbol m underscore pi now exists. Right? You can give it a value like this. And so what the preprocessor will do is that whenever it sees m pi, it will substitute this value into your program for you. Right? So everywhere you write m pi, so here, the preprocessor grabs this and replaces the symbol with the value. So that's all define does. The compound statements are all, I think they're all more or less the same as in Java, except for perhaps the switch statement. If statement works exactly the same as in Java. Right? So if condition, else if, some condition, else. Right? Exactly the same as in Java. Switch, we don't really don't talk about in 124. It exists in the Java language. It's slightly different in C because you can't switch on the same things that you can switch on in Java. If you want to know how to use a switch statement, just click on that link there and look at it. You can think of a switch statement as a giant if-else-if statement. I think in C it only works for integer types, so you can only switch on integer values. But you can just hit that link there if you want to know how to use a switch statement. While loops work the same as in Java. Do while loops work the same as they do in Java. Right? For loops work the same as in Java, except there is no for each loop in C. Right? So in C, you only have the counting style loop here. Right? And of course, you've got break and continue, just like you've got break and continue in Java and Python. Right? So that notebook there is mostly for completeness. The only significant thing here is the no assignment to array variables. Okay, hopefully there's no questions there. And I guess that takes us to the next notebook, which is the integers. And so there is some new content here, surprisingly. Sorry. All right, so the integer types in C are similar to the integer types in Java, but there are some important differences. So one of them is that Boolean in C is different than Boolean in Java. Right? So bools are true-false values in C are integer values. Right? So false is 0. Anything not 0 is true. Sorry. The unusual thing, if you're a Java or a Python programmer, is that the C standard doesn't say how your integer values are represented. Right? So the standard doesn't say that your integers are even binary. It doesn't say anything about its representation. Right? So you don't know if it's 1's complement, 2's complement, sign bit, or some other magical representation that your CPU manufacturer has decided to come up with. Right? And this is because of the era in which the language was created. Right? So when C first arrived, or started to arrive, there were multiple CPU manufacturers, each of which would represent values on their CPUs in a different way. Right? So nowadays, everybody is more or less settled on using what's called 2's complement to represent integer values. So C23 is supposed to say that integer values are in 2's complement. I don't know if that actually has happened yet or not. If you don't know how your integer values are represented, overflow might behave differently depending on what computer you run your program on. And so even integer overflow doesn't behave the same on every computer in C. Although if you're running it on a modern computer, it will behave the same way. Another thing is the standard doesn't say how big an integer is, right? So it doesn't say how big an int is, it doesn't say how big a short is, it doesn't say how big a long is, right? It doesn't tell you how many bits are in any of these values, right? Whereas Java is very specific about how many bits are in each of those types. There are more types in C, and C is more permissive than Java when you convert between types. So you can silently convert between long and int in C without any issues. Whereas in Java, if you try to store a long value in an int, the compiler will complain. Right. All right, so there are more integer types. We don't use most of them, right, in this course. So mostly we use int. Occasionally we use long or long int. It doesn't matter what you call it. Of course, you use char because we're going to work with strings, and we're going to use bool because we're going to work with true-false values. The unsigned types also show up, and so they're also relevant to us. So notice here how many bits each value occupies, not specified by the language. Right? The language only says that the size of these things goes in a certain order. Right? So char is at least as big as bool. Short is bigger than char. Short is bigger than or equal to the size of char. Right? Int is bigger than or equal to the size of short. Long is bigger than or equal to the size of int, and so on and so on and so on. It's still true, though, that these are primitive types, so they occupy a fixed amount of memory. Right? And that means there's some minimum value and some maximum value that they can represent. This also means that overflow occurs in C. Right? So if you try to compute some value in int that exceeds the range of int, you get overflow. Right? And that's true for all of the types, all of the integer types. So in Java, there's no unsigned type. Unsigned types in C simply cannot be negative. Right? So their values go from 0 up to some positive maximum value. If you go past 0, you wrap around to the largest maximum value on a modern computer. Okay, so bool we saw earlier. Bool is C's Boolean type, right? So it's a logical true or false. If you want to use bool, you have to include standard bool. Right? If you forget to include standard bool, the compiler will complain, and it wants you to use the type _big B bool. Right? If you ever see anything start with an underscore, that means it's a feature that was introduced to the language in a later version of C. Right? So its official type is _big B bool. But I think most people just include standard bool and write it as bool because it's a lot easier to read that way. You can use the symbols true and false for bool, but they're really just the values 1 and 0. Right? So here, this prints true if the flag is true and false if it's not. Right? So if you put in false here, it prints false. Right? It's a numeric value, so you put in 0, that's fine. Right? If you try to do this in Java, Java doesn't let you do this, right? Java doesn't allow conversion between Boolean and integer values. If you use 1, that's true. But what you have to remember is that any non-zero value is true. Right? So -1 is also true. Right? And even though I just told you it's an integer value, the compiler doesn't care if you use a floating point value here either. It simply converts it to true or false, right, to 1 or 0. So that gets converted to 1, and then this prints true. Right. Char is the type that represents characters in a string. There's also an unsigned char and a signed char, and they all are considered 3 distinct types in C. So the standard says char is equivalent to one of these two, but it doesn't say which one. So your compiler writer is free to decide whether or not their characters are represented as unsigned values or signed values. Right? The compiler writer has to decide on which, but they don't have to tell you. So they are considered 3 distinct types. Normally we're just going to use char and not worry about it. Okay, the unsigned integers. So these things start at 0 and they go up to some maximum positive value. Right? So they have the simplest binary representation. I'm assuming you guys know what binary is. That's true, right? You know how to work with binary numbers, yes? Basically? Okay, so this is all that you really have to remember is what order are we going to write our numbers in. So we're going to write them from right to left, from most significant bit to least significant bit. Right? So the number 0, 1, 1, 1, blah, 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 right, is, so starting from the right-hand side, right, that 1 is multiplied by 2 to the 0, right, the next value is multiplied by 2 to the 1, and the leftmost value is multiplied by 2 to the 7. Right? Most significant bit because that bit contributes the most to the magnitude of the number. Right? Least significant bit because that bit contributes least to the magnitude of the number. And of course, to convert this to base 10, you just multiply all these things together and then add them up, right? And you get the sum of 107 here. So I'm always going to write these from left to right, most significant bit to least significant bit. You have to remember that not everybody writes binary numbers this way. So you can write them in the other order. You can write them from least significant bit to most significant bit. I'm always going to do it, though, from most significant bit to least significant bit. Okay, so for the unsigned numbers, right, the number with the smallest magnitude is obviously all zeros, right? Makes sense, right? That's 0, right? If the value is unsigned, all of these multipliers are positive. So the largest unsigned binary value is simply all 1s, right? So for an 8-bit binary number, that's 255. Right? And of course, you can prove by induction if you have n bits, then the largest value that you can represent is 2n minus 1. I'm not going to ask you to do it, but it's pretty easy to do. Okay, so what about the sign values? So the sign values are, in today's computers, are almost always represented in what's called 2's complement. Right? It's exactly the same as what I just described, except the most significant bit is considered to be negative. So if it's 0, you have a positive number. Right? If it's 1, then you have a negative number. Right? So the multiplier on the most significant bit is negative. That's 2's complement representation. Pretty much every modern computer uses 2's complement for integer values. Certainly every modern desktop computer. I guess embedded devices, that may not necessarily be the case. Okay, so 0, 1, 1, 0, 1, 1, 1, 0, 1, 1. We know that so if you look at the most significant bit, it's 0, so we know this is positive. Right? That's the same binary number as the previous example, so its value is 107. Right? If you make the first bit a 1, then you have to add in minus 128. So now you've got a negative number, right? It's negative 21. Okay, so what's the most positive 2's complement integer number? Right? So the most positive unsigned integer number is all 1s. Right? For a 2's complement, though, the most significant bit is negative, or its multiplier is negative. So the largest positive value starts with a 0, right? Then has all 1s. Right? So it's 127 in 8 bits. Right? The most negative value, so remember all of these other bits, their multipliers are positive. So the most negative value, there has to be a 1 in the first bit, right? And the remaining bits all have to be 0. Right? If any of the other bits are 1, then you're adding some positive value. Right? So the most negative value is minus 128. Right? Notice that the range is not symmetric. Right? The largest positive value is 127. Right? The most negative value, its magnitude is 128. Right? Which is a problem. Right? Why is it a problem? Right? So the problem is, if you start out with minus 128 and you negate it, right? So if you take x and you write minus x, right, the value of minus x may not exist. Right? If x is minus 128, mathematically negative x is 128, which doesn't exist in 2's complement. Right? So simply negating a value can cause overflow in 2's complement. Right? And all the others are exactly the same thing. Right? So multiplying by negative 1 may not work. Dividing by negative 1 may not work. Right? Taking the absolute value of x may not work. And this is all a consequence of deciding to use 2's complement as your representation. Right? So in C, if these happen, right, then what you end up with is undefined behavior. So the language doesn't say what the actual value is if the value shaded in gray doesn't exist. Right? And so undefined behavior simply means anything can happen. Right? The program will run. It might crash. Oh, in this case, it probably won't. But it will compile. The compiler may or may not issue a warning. Right? It doesn't have to. And it may not always be able to detect that this error is occurring. So what happens if you actually try to do this? So scar_min comes from the header file limits.h. Scar_min is signed car_min, so the smallest or the most negative signed car value. Right. So this is going to be our most negative value. I'm going to try to negate it here. I'm going to take its absolute value there. I'm going to multiply it by minus 1 there. I'm going to divide by minus 1 here. So let's see what happens. So signed car_min is minus 128. So on my computer, it looks like I have an 8-bit car. So its most negative value is minus 128. That makes sense, right? Apparently, minus 128 is also minus 128, right? The absolute value of minus 128 is also minus 128. Right? Multiplying minus 128 by negative 1 yields minus 128, right? And dividing minus 128 by minus 1 also yields minus 128. Right? These are consistent with what's with overflow in this particular for this particular example. So this is doing what most programmers think would happen. The output is not guaranteed, right? So you're not guaranteed to get those values there. Okay, so if you have if you're working in 2's complement, there is a relationship between x and minus x, and so it's relatively easy to get the negative value or to negate a value in 2's complement, assuming the negation actually exists. Right? So for almost any integer value, right, you can compute minus x just by flipping the bits of the number. So zeros become ones, ones become zeros, and then you add 1 to the result. Right? So if I take the binary number 1, right, I want to get negative 1 from this. Right? So I can flip all the bits, Right? So starting with all zeros and then a 1, flip the bits, you get all 1s, right? The second row here, and a 0. Right? Now add 1 to that number there. So 0 and 1 is 1, right? 1 and 0 is 1, and so on and so on and so on. You get all 1s. Right? So all 1s, remember in unsigned, that would be the maximum. That would be the maximum positive value. In 2's complement, it's the value minus 1. Okay, another example. Here's 56. So 0, 0, 1, 1, 1, 0, 0, 0. Right? I want to compute negative 56. So you flip all the bits. So I get 1, 1, 0, 0, 0, 1, 1, 1. Now add 1. Right? So 1 and 1 is 0, carry the 1. Right? 1 and 1 and 0 is 0, carry the 1. 1 and 1 and 0 is 0, carry the 1. Right? And then you get a 1, 0, 0, 1, 1. Right? Compute the result, and you get minus 56. Right? And so when you write something like minus x on your computer, there's a pretty good chance that on a modern computer, internally what's happening is the bits are flipping, and you're adding 1 to the value. Right? Okay, so standard lib.h. So there are some mathematical functions, in particular absolute value, that are defined in standard lib.h instead of math.h, and I don't know why. Doesn't make any sense, but they're there. Right? They're in standard lib instead of in math. So remember that in C, 2 identifiers can't have the same name in the same program. So if you want the absolute value of an int, the function that you're calling is different than the absolute value for a long int or for a short or for something else. Right? So here I have an int value, I have a long int value, and I have a long int value. Right? If I want to compute the absolute value of all 3 of these things, it's 3 different functions. Right? So the absolute value for an int is just called ABS, which is nice. There we go. Right? The absolute value for a long int is LABS, right? And the absolute value function for a long value is LLABS. Right? So there is no function overloading in C, right? Whereas there is method overloading in Java. So when you're looking inside of the standard library functions, you'll see a lot of functions that have similar names, right? So typically it differs by 1 letter somewhere, right? And that's because if you want to call the function with different types, you need a different name for the function because C doesn't allow function overloading. All right, I think that's plenty for today. So we'll call it quits there, and we'll pick it up in the next notebook in the next lecture. So just a reminder, on Thursday you do have your midterm. Your midterm is all bash. And I think there are multiple examples of old midterms and tests already on Q for you to look at. Right. So that'll be Thursday in class. Any questions about the midterm?